Hello everyone, welcome to this lesson. In today's tutorial, we are going to simulate heat exchangers in Aspen Plus. And the objective of today's lesson is that you will develop a fundamental understanding of heat exchanger, and you will know how to use heater model in Aspen Plus and how to use HeatX model in Aspen Plus, and what is the difference between these models, and when we use heater model and when we use the HeatX model. So before going to the simulation, I will just briefly review about what is a heat exchanger. So heat exchanger are devices which are used for efficient heat transfer, and heat exchanger are used in almost every chemical process industry. They are used in power plants, refrigeration, HVAC system. So as I told earlier, that they efficiently transfer heat between two fluids without mixing them, and the heat transfer mechanism is by conduction, convection, or combination of both. So the two types of heat exchanger which are mostly used, which are used widely in the chemical process industries, they are the shell and tube heat exchanger and the plate heat exchanger. So this is a typical shell and tube heat exchanger. Here you can see that bundle of tubes is installed inside the shell casing. So one of the fluids, say hard fluid, move in the shell, okay, to this path, and the cool fluid enter into the tubes. So the hard fluid thus transfer it heat to the cool fluid, and then it is collected here. Similarly, the cool fluid which move in the tubes, this fluid receive heat from the hard fluid and thus is collected here. Okay, these are called baffles. They are installed to support the tubes, and they also cause the turbulency for better heat transfer. There are some advantages and disadvantages of this type of heat exchanger. The advantages is that they can handle high pressure and high temperature. Yeah, they can withstand high temperature and high pressure, and they are easy to control and operate. However, there are some disadvantages as compared to the plate and frame heat exchanger. This surface to volume ratio is small, and another is they are very hard to maintain, because when some fouling is developed here, like when there is some scaling on this inner side of the tube, so they are very hard to clean. And another type of heat exchanger is plate heat exchanger. So in plate heat exchanger, we have these plates, and they are fixed inside a frame. So the cooled and the hard fluid moves on the alternative side of a plate, like you can see here, that the cooled fluid enter here, and the hard fluid enter here. Thus these fluid transfer the heat across this plate, and thus the cool fluid is then collected here, and the hard fluid is collected here. The advantages of these plates, that they have higher heat transfer area. They are compact, which means that they have higher surface to volume ratio, and they are easy to clean. However, there are some disadvantages. They are not suitable for process with high operating temperature and pressure, and they have high capital cost. And another disadvantage is that the pumping costs are very high, because as compared to the shell and tube heat exchanger, the pressure drop in the plate heat exchanger is higher. And the heat exchanger can also be classified based on the flow configuration. One is called the co-current flow arrangement. So here the hot and fluid enters from the same side of the heat exchanger. Just like here, if this plate is a co-current, so in that case, the hot fluid and the cool fluid both enters at the same end. So as the hot fluid move along the length along the heat exchanger, the temperature decreases, and as the cool fluid move, its temperature is increasing. Co-current has the disadvantage that the delta T temperature difference is not constant, and as you can see that the temperature difference is higher here, or the temperature difference decreases along the heat exchanger. Another one is a counter current flow arrangement, as you saw in the Shell tube heat exchanger. That was the counter flow arrangement where the hot fluid enters from one side and the cool fluid enters from another side. So you can see that as the cool fluid moves along the length of heat exchanger, its temperature is increasing while the temperature of the hot fluid is decreasing. So the advantage of this counter current arrangement is that the delta T temperature difference between the hot and the cool, it remains the same, while here the temperature difference decreases. So now we are going to simulate a case study in Aspen Plus, and we are going to cool this paver in butanol, which is produced at a rate of 1000 kg per hour in 2 bar from an upstream distillation process. So we want to cool this in butanol from 117.7 degrees C to 40 degrees C, and this is done with the cooling water which is available at 25 degrees C and 2 bar. So we are going to model a heat exchanger in Aspen Plus to determine the required cooling duty. What is the cooling duty when this is temperature is reduced from 117 to 40, and what is the amount of cooling water required? So is the we don't know that what is the flow rate of water, so we will determine this flow rate of water using the design spec picture in the Aspen Plus. So we will first use heater model, and then we will use HeatX model to simulate this case study. So open Aspen Plus. Aspen Plus. Okay, I am doing this in Aspen Plus v14. You may do this in version 8, 9, 10, 11, 12 or a later version. Click on new and select this user and metric. So click on open selected template. Okay, add your component here. So water, and another is butanol. And now click on the methods, and here just use Wilson model. Okay, it is asking you to confirm a few things, so just click on this parameters and then click on binary parameter. It is asking you to confirm these parameters, these binary parameter, right? So now click on simulation, and first I will use just simple heater model. Click on this exchanger and install this heater model. Okay, let me call this cooler because we are cooling the butanol, and this is the input stream and this is the output stream. Let me call this B but in, and this we call this but out, right? And double click on this butane, and the temperature is 117.7 degrees C, pressure is 2 bar, and the mass flow rate is given, mass flow. So this is a 1000 per hour, right? 1000 kilogram per hour. Okay, and now view flow sheet and double click on this cooler, and we want to cool this, so we are giving the temperature, so here that's why temperature is selected. If you are given the duty, then you should select the duty. If you are given the temperature change, then you need to select the temperature change, and if you are given the vapor friction, like we want to reduce this to, say, maybe this is vapor, and we want to reduce the temperature to saturated liquid. So in that case, you will select the vapor protection, and then you will enter 0 as the vapor protection here. However, we are given the outer temperature and pressure. So the temperature is 40 degrees C. We want to cool this to 40 degrees C, and there is no pressure drop, so just enter 0. Now run this. When you run the simulation, click on the results, and this is the, just let me change this to kilowatt. So this that means that we need to remove 69.4723 kilowatt in order to down the temperature from 117.7 to 40 degrees C. Okay, now let me install this heater, because we are using water. So let us see that how much water is required in order to cool this from 117.7 to 40 degrees C. So I will call this heater, and just flip this, click on R, again R. Okay, so R actually rotate this. So here we call this W in, water in, and this W out. Just click on escape to exit the stream mode and call this W out. Okay, and this W in, it is given as this we are given the temperature, which is 25 degrees C, available at 25 degrees C. Pressure is 2 bar, and the flow rate is a mass flow is 600. The mass flow rate is not given. Let me just guess some value, and let me just enter 600 kilogram per hour, right? And now go back to that view sheet, and okay, this heat which is released by this cooler is actually absorbed. Which is released by this stream is absorbed by this stream. So for that, click on this button and click on this heat stream. So the heat which is given by this cooler is actually absorbed by this heater. So that's why I have connected this cooler and heater through a heat stream. Okay, this is heat stream, this dash line, and this is material stream. Okay, if I double click on this heater, you will see that only the pressure, this you need to specify only one condition, because the other is already specified. Now it knows that it knows the heat duty. So another is pressure, there is no pressure drop. Okay, and now it knows that the heat duty that it is receiving is 69 kilowatt from the cooler. Okay, now run the simulation, and here you can see if I click on this W out, temperature is 120 degrees, right? Let me just click on this flow sheet, and let me just click on this temperature. You can see that W out is a temperature is 120 degrees C, and this is 117.7 degrees C, which it has rounded up to 118 degrees C. So actually there is now a problem. There is temperature crossover. This is not possible thermodynamically. If I want to pass these two stream through a Schilling tube heat exchanger, so this is not possible, because the cooled water temperature cannot exceed this temperature, the input temperature of butanol, because this stream is actually receiving the heat from this stream. So this is not possible. Therefore, the temperature of this stream will be higher from this butanol stream at any location. So there is a temperature crossover. That means that we need to increase the temperature, the flow rate of this input stream. So just double click on it, and let me choose 8. Let me write 800 kilogram per hour. Then again simulate it. view the sheet. So while click on modify and then check this temperature, so you will see the temperature. Now this is thermodynamically possible, right? If you match these two streams in a shell and tube heat exchanger or double pipe heat exchanger, now this is possible because the input temperature here is 118 and here the output temperature is 98 degrees C. Means that temperature difference is 20 degrees C here. Earlier the temperature difference was -2 degrees C, which is not possible thermodynamically. So let me determine the water flow rate. I want that this temperature must be 10 degrees C, right? Not greater than 10 degrees C, not less than 10 degrees C. So what should be the flow rate of water? So you saw that the flow rate is somewhere between 600 kilogram per hour and 800 kilogram per hour, right? So I will use the design spec for this. So go to the flow sheeting option in this navigation tab, click on design spec, click on new DS1. Okay, here I will define some variable. The first variable is this is, let me call TI. This is the input temperature of the butanol, right? So this is a stream variable, right? This is a stream variable. Stream variable, which stream? Butane. Which variable? This is a temperature. And of course, this is in the unit is degree C. Okay, another variable, click on new and let me call this T out. Here by TO I mean the outlet temperature of the water. So this is again stream variable. And which stream? W out, right? Which variable? Temperature, and the units is degree C. Now click on spec and here I shall write TI minus TO, TI minus TO, and the difference, sorry, this is TI minus TO. This difference must be 10 degrees C, and you need to provide some tolerance because sometimes the software is unable to obtain the exact value, so some tolerance must be provided here. And now, so this temperature difference must be 10 degrees C with this tolerance. Vary. What should we vary? So this is again stream variable. Stream variable. Which stream? Wn. And which variable? Mass flow rate. From 600 to 800. So now it will search the value from 600, between the 600 and 800 kilogram per hour, input water flow rate, and it will search it until this TI minus T naught is a 10 degrees C. So let me just click on run, and here you can see the result. Just click on this design spec D's result. So the flow rate is 697.608 kilogram per hour. So in that case, like if you click on view and click on flow sheet, here you can see that the outlet water temperature is just click on this result. This is 107.7 degrees C, and this butane, this temperature is 117.7 degrees C. You can also check in the results. So now the temperature difference here is 10 degrees C. So for the 10 degrees C temperature difference, this flow rate must be 697 kilogram per hour. If you double click on this Wn, we have provided 800 kilogram per hour. However, if you check the results, so this is actually 697.608 kilogram per hour. Let's suppose if you are using plate heat exchanger, so this temperature difference may be 5 degrees C. In that case, we will go to the design spec block, design spec, click on input, and this TI minus T naught, let me just change this to 5 degrees C, and then simulate this again. Okay, and if you check the results, in that case the flow rate of the water is 655 degrees C, and here you can see that T out, this is the water outlet temperature is 112 degrees C, and the input temperature of the butanol is 117.7 degrees C. So the temperature difference is now 5 degrees C. I will change this to 10 degrees C, and we are using, suppose, the shell and heat exchanger. So the flow rate is 697, and these are the input and the output, the input temperature of butanol and output temperature of the water. Okay, now let us do the same thing in the HeatX using the HeatX model. So I will do that in a new simulation. So click on File, click on View, and this user metric, and select this general with metric units and click on Open. Selected. I don't want to close this. Click No. So when it opens, first add the these components. So one is water and one is butanol. Now go to the methods, click on specification, and here select the Wilson model. And click on this parameter. It is asking you to confirm these things. So this binary parameters, and then click on Wilson. It is asking you to confirm these binary attrition parameters. Now click on simulation. In the simulation, click on the exchanger and install this HeatX model. And let me call this HeatX. Okay, and this is the cold stream. I will call this WN. Okay, and this is the cold stream out. Okay, similarly, this is the hot stream in, and this is the hot stream out. Okay, I will call this W out. This is water out. This butanol input, and this is but out. Right? We know that butanol stream is hot stream and the water stream is cold stream. So now double click on this butanol stream. We know the temperature is 117.7 degrees C and the pressure is 2 bar. Mass flow rate is given, so this is 1000 kilogram per hour. Similarly, now just click on this WN to specify this. Temperature is 25 degrees C and the pressure is 2 bar. And we don't know the mass flow rate. Of course, we have calculated this for the heater model, which was 697.7 kilogram per hour. However, we will again here we will use the design specs, and design specs will do the calculation for us. So let me just enter 600 here. Let us assume that this is 600 kilogram per hour. And now click on View, Flow Sheet, double click on this HeatX block, and the calculation mode is design. Calculation mode is design, and the model fidelity shortcut. This design mode, and specification. So we know the outlet temperature, so select the hot stream outlet temperature. If this outlet temperature decreases given, or if you know exchanger duty or something else, then if you know the cold stream outlet temperature, then you should select that. However, here we know the hot stream outlet temperature. This is 40 degrees C, and this is in the design mode, which means that it will do the design calculation for us and it will calculate area for us, right? So if you just now click on the run, so we get the error. Let me check what is the error. Okay, before we run it, just do minimum approach temperature, change this to 10 degrees C, right? Change this to 10 degrees C. That means that at any location, the temperature between the hot stream and the cool stream must be 10 degrees C. So run this again, and we get the error. Click on this OK, and let us check that what is the error. So it says that temperature crossover is detected. Recalculating with minimum temperature approach spec. Just click on this thermal results and then summary. So here you can see that it is unable to achieve this. Butanol input temperature is 117 and the outlet temperature is 51 degrees C. Okay, that means that if you want that this temperature difference but in minus W out, which is this temperature difference, if you want this to be 10 degrees C, not less than 10 degrees C, then this is what you can achieve. You cannot cool this from you can cool this to 51.7 degrees C. You cannot cool this from temperature which is lower than this temperature. So, and here you if you just click on this heat duty, check this in kilowatt. So the heat duty is 59 kilowatt, and you saw earlier in the heater model that in order for this hot stream to achieve its desired temperature, which is 40 degrees C, this duty was 69 kilowatt, right? So that means that 600 kilogram is kilogram per hour. That was not enough. That flow rate was not enough, right? So now if you click on this thermal results and you click on this TQ curve, you can also go to here TQ curve, and if you want to increase the number of points, you can do it from here, and then click on this. If you want to see the numbers, so these are the number, and in the table format, and if you want to see the curve, so this TQ curve. So these are the TQ curve. So the temperature crossover is actually, this is at this point, where full temperature is 107 and the hot temperature is 117.7 degrees C. So now what should be the temperature? So for that we shall actually use the design spec. So click on the design spec and click on new. Okay, so I will TI the input temperature of the butanol, and this is a stream variable, right? And which stream? butane. And which variable? This is temperature in degree C. Okay, another is just copy and paste this. So we have copied that variable, call this TO. Okay, this TO. Okay, here it is TO, right? And now this is output temperature of water. So select this, change this butane from W out, right? So T out is actually the outlet temperature of water, and TI is the inlet temperature of the butanol. Now click on spec, and this TI minus TO. This is target is 10 degrees C, and the tolerance is 0.0001. And click on vary. So what will be vary? This stream variable. Okay, which variable? The which stream? The input water stream, and the mass flow rate, and from 600 to 800, right? So it will do calculation for us. Just click on run. Okay, now again we got the problem. So if you click on OK, so it's, and click on HeatX, so it says that actually there is problem, because it has started from 600 kilogram, then it is checking 601, 602, but it has encountered problem at 600 kilogram, because you saw that there was temperature crossover in the 600 when the flow rate was 600 kilograms. So it has stopped the calculation. So we shall go to the setup, and then we shall go to the option in the HeatX block, and then convergence, and here we shall click allow temperature crossover. So now the temperature crossover is allowed. Now it will do the calculation, and it will find the desired number. So just click on run, and here now the results are available. So just go to the design input, the results, and here you can see that the manipulated variable, which is the water flow rate, this is 697.607 degrees kilogram per hour, and the outlet temperature is 107. This is of course the water outlet temperature, and this is the butanol input temperature. If you now click on the thermal results, so input of the butanol, output temperature, right? And this is the input and output temperature of the water, and this is the heat exchanger, the heat duty. This should be 69 kilowatt. So this is just select kilowatt, and you can see this is the same as we calculated in the using the heater and cooler model. If you click on the exchanger detail, so it is giving you the this is the heat duty, and this is the area, 6.62 square meter, and it is also calculating the LMTD for you, which is a 12.3314 degrees C. Okay, now deactivate this design spec block. Right click on it and click on deactivate, and click on this WN input stream, and set this to 700 kilogram per hour, because we already got the result. So just put this to 700 kilogram per hour and deactivate the design spec feature. Now go to the HeatX model. Okay. So and now I will simulate this under the rating. Okay, rating means that let's suppose we already have a heat exchanger. Let us say the area of that heat exchanger is 8 square meter. So when you select rating, you need to provide the area as well as some specification. So we know that the outlet temperature is 40 degrees C, and we have a heat exchanger. This heat exchanger has 8 square meter area. So I will check that is my heat exchanger, is this over designed, or this is under designed. So that means that is this 8 square meter heat exchanger is enough to do the job, or is this a bigger, or is this smaller? So run the simulation, and in the HeatX, click on the thermal results and click on the exchanger details. So here you can see that the required heat exchanger area is 6.54 square meter, right? Of course we calculated this earlier as well. So it says that your design, this is actually over design with a 22.1865% over design, right? So that means that this is this heat exchanger is bigger. It's a bigger heat exchanger. Let me just change this to setup and rating and write like 3 square meter, right? And let us suppose that we have a heat exchanger which is 3 square meter. Let me check that if it can do the job. So run it, and you click on the thermal results. So you can see that there is a negative sign here. That means that this is under design, 54.18% under design. Last time there was no negative sign. This was 22%, right? So that means that this area is not enough to do the job, right? Now again click on this setup, and let us run this under simulation mode. So here select the simulation. Simulation means that let's suppose you have a heat exchanger, and you want to see that if we use this heat exchanger, let's suppose I have a heat exchanger which is 5 square meter, and if I use this heat exchanger where the input temperature of the hot stream is 117.7 degrees C, and the input temperature of the cold stream, which we specified, was 25 degrees C. And if I passed these two streams to a heat exchanger which has a area of 5 square meter square, so what will be the output temperature of the hot fluid and the cool fluid? So if I run this, and if I now click on the thermal results, so you can see that this heat exchanger will only reduce the temperature from 117 to 43 degrees C. This will not be able to achieve that desired temperature. And here you can see the water temperature is raised to 104 degrees C. Let me just use another heat exchanger under simulation mode, which has 4 square meter area. Run this again. Click on the thermal results. So it will down the temperature to 46 degrees C only. Now, why we need to have some why we need to use the heater block instead of this when we need to use this, and when we need to use the HeatX block. So here you can see the HeatX block is used. A feed stream, it is preheated, and it is passed through a distillation column. Okay, and this the product which is coming out the reboiler, this is used as hard stream, and it is actually preheating this feed, right? So there is, if we use to simulate this processing with the HeatX blocks, we may encounter some problems, because in order to simulate the column, first we need to simulate the HeatX block. However, before we simulate the HeatX block, I need the results of this stream. And how can we obtain the results of this stream? Of course, we need to first run this distillation column block. So that means that there we will have some this is a convergence problem, right? So because prior to the simulation of this distillation block, you need to simulate to run this. However, before running this, you need to run this. So maybe you may encounter some convergence issues. However, if you use these heater blocks, you don't have any such issue, because first we will this feed stream, and then you will use some heater block, right? And first this will run, then the distillation column will run. After that, this heater block will run. So we will not encounter any convergence issues here. So this is a good idea to first use this combination of these heater blocks to determine this outlet temperature and to determine the heat duty, and after that you may use this HeatX block, right? Thank you very much. If you have any question, please put this in your comments, and I shall try to answer your question. Thank you very much for watching this video. Please like this video, share with your friends, and also subscribe this channel. Thank you very much.